So let's start with the principle of conservation of energy. Now, what this principle says? Okay, this is the principle of conservation of energy. This is one of the most fundamental principle of physics. It is the principle of conservation of energy. We will start our discussion with talking about the statement about it. You all are aware about it. In 9th standard also we have discussed about it. So what the principle of conservation of energy says? It says that energy can neither be created nor it can be destroyed. It only changes from one form to the other. Exactly. The total energy of the universe always remains constant. Okay, so this is what the law of conservation of energy says. It says that it can neither be created nor it can be destroyed. It only changes from one form to the other. Again, very basic explanation about conservation of energy. If there is only an interchange between the potential energy and kinetic energy, if we are only talking, this is a if part, means if we are only talking about the interchange between potential energy and kinetic energy, then the total mechanical energy, that is the sum of kinetic and potential, always remains constant when there are no frictional forces applicable. So if there is no friction involved, then you will find that the total mechanical energy always remains constant. Okay. If there is only an interchange between potential energy and kinetic energy. Okay. So we start with our very basic. Please write down this, all of you. Please write down. Okay. Where there is no fixed. So the principle of conservation of energy is one of the fundamental principles of nature. As I told you in the beginning as well, that this is something which is a very fundamental principle of nature. This is a very basic and a fundamental principle of nature, the law of conservation of energy. Please copy this. Whatever queries you may be having in this topic, please type your query in the chat. Okay. So let's start with the derivation of this conservation of energy. Okay. We are having a very fundamental and a very basic derivation of this topic. So let's take this example. Okay. What we are having, we are looking at the total energy remains constant. The total mechanical energy, that is the sum of the kinetic energy and potential energy, remains constant. So the topic of our discussion is the theoretical verification of the sum of kinetic plus potential is constant. Okay, and what we are doing, we are considering the case for a freely falling body. So we are having this object of mass m, and it is at a height h, and then we drop it, we just release it, and then this object is falling, and at different instants we will find which are those instants. At a, at b, and at c, you will find that the total energy, that is the total mechanical energy, the sum of kinetic plus potential, will always remain constant. So we are considering that the body, this is the body of mass m, be falling freely under the gravity from the height h. So it is falling freely from the height h above the ground. So what is the height it is having? It is having the height h above the ground. As the body falls down, its potential energy changes into kinetic energy. Very true, very fundamental idea, that it is here as the object starts falling down, you will find the height from the ground will keep on decreasing, the h parameter will keep on decreasing, so its potential energy will keep on decreasing, because what's the potential energy formula? Mgh. So here m and g will remain constant, but h will keep on decreasing. So as the h parameter keeps on decreasing, its potential energy will keep on decreasing. But this potential energy will get converted into kinetic. How? Because when the object is at the top, it has zero kinetic energy because the object is at rest. We are holding the object over there at point. So at that time, the velocity of the object is zero. So if you see the formula for kinetic energy, it is half mv square. So at the top, the velocity of the object is zero. So kinetic energy is zero. But as we release it, it starts falling down. And we know when the object falls, it accelerates due to the it accelerates, okay, because the earth is trying to pull that object towards itself, so it will accelerate. And we know very well, when the object accelerates, its velocity keeps on increasing. So if you look at the formula of kinetic energy, it is half mv square. So half and m, these are going to remain constant, but v square, velocity will keep on increasing. And as the velocity will keep on increasing, its kinetic energy will also increase. So to sum up the topic, as the object keep on falling down, its potential energy will keep on decreasing, but at the same instant, the kinetic energy will be increasing. So the entire potential energy or the potential energy will keep on changing to kinetic energy. So what we are looking at? We are looking at that at each point of motion, the sum of kinetic energy and potential energy remains unchanged, or it remains the same. Now we start our discussion of three positions. As I told you in the beginning that we are going to discuss the sum of the kinetic and potential at A, at B, and at C. So let's start with at A, which is at the height above the ground. So initial velocity of the body is zero, because we are holding the object here. So how much is the initial velocity? Zero, because the body is at rest. Okay. So how much is the kinetic energy? So the kinetic energy will be zero. Why? Because we know kinetic energy is half m v square, but the velocity is zero. So the entire term will become zero. So the kinetic energy is zero. How much is the potential energy? So let's talk about how much is the potential energy at A. The potential energy is mg, and the height. How much is the height? H is the height. So the potential energy is mg. Okay, so now we'll find out the total energy. The total energy will be K plus U, means 0 plus mg. So how much is the total energy? The total energy is mgh. Okay, please copy this beta, because we are having this derivation for exams as well. Okay, so write down the total energy is mgh. This is very important. I had given it a star. Remember, at position A, at a height above the ground, the total energy is mgh. This is for A. Now we will look at for B, as well as we are going to look at for C. Okay, so write down at A, the total energy is mgh. If you have copied it, please type yes in the chat so that I can proceed. Okay, chalo. So all of you keep on responding beta. Okay. Now we will look at the second case. Okay, that at position B. Okay, so let's talk about the second case now at position B. At position B, when it has fallen a distance x. So now from A, the object has started falling, 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 and it reaches to the point B. And how much is the how much it has fallen? It has fallen the distance x. Okay, you can see in the diagram as well. In the diagram part, you will find that it has fallen the distance. Now let's find out at B, how much is the total energy. That is, how much is the total mechanical energy. That is the sum of kinetic and potential. So we start with, now how much is the velocity. So let V1 be the velocity acquired by the body at B after falling through a distance x. Understand? The object is falling now, and as it is falling, it has acquired some velocity. So how much is the velocity it has acquired? V. After falling through a distance x. Okay, now see what I have taken. What is the initial velocity during this case? The initial velocity is 0. Okay, try to understand. Our initial velocity is 0. Okay, because when we drop it, it was at rest, so initial velocity is 0. How much is the displacement of the object? So you will find the displacement is x. Why? Because it has displaced through this much distance. X. It has fallen through this much distance. X. And how much is the acceleration? So acceleration is equal to the acceleration due to gravity, that is g. Okay, so these are the three consideration. Now let's find out. Now we are using the same equation. Yesterday also we used the same equation. V square is equal to u square plus 2a. In the for the derivation of kinetic energy, for work energy theorem, and now for this as well. We are using this equation only, v square is equal to u square plus twice as, because the time parameter is unknown to us. So we are using this equation. Okay, so now what is the velocity? Initial velocity is 0. So v square, sorry, not in final velocity, sorry. Your v square is as it is. Your initial velocity is 0. So your u square becomes 0. So v square is equal to u square is 0. So 0 plus 2. Then a is what? A is the acceleration due to gravity. So my a has been replaced by g, and my s, which is the distance, is equal to the display is equal to x. So here my equation becomes v square is equal to 2g x. Okay, so therefore we get this equation v square is equal to 2gx. This is our equation. Now what we will do, this equation we will put it in the kinetic energy, because I want to find out how much is the kinetic energy. So kinetic energy, we know the formula is half m v square, which is equal to half m. Now v square is 2gx. In this equation we calculated. So instead of using v square, I have put here 2g x. So instead of v square, we put 2gx. Now what happens here, you will find that this 2 and this 2 gets cancelled. Okay, so what we are left with then? So we are left with mgx. So how much is the kinetic energy at the point B? The kinetic energy at the point B is mgx. Remember, what is the kinetic energy at B? The kinetic energy at B is mgx. Now, at the height B, the height from the ground is h minus x. How it is? Remember, h is the total height and the object has displaced by x. So if h is total and this distance is x, so how much is the remaining part? So the remaining part will be h minus x. So this is h. It has displaced through x. So the remaining distance is h minus x. So how much is the height? So height is h minus. So let's find out the potential energy. So potential energy is mgh, but here I cannot use h because it is not at a height A, it is at a height B. So at B, the height is h minus. So how much is the potential energy? The potential energy is mg h minus. How much is the kinetic energy? The kinetic energy is mgx. So what we will do? Potential and kinetic, let's add it. So total energy will be kinetic plus potential. Kinetic is how much? Mgx. Potential is how much? Mg h minus x. Okay, so if you simplify it, you will find, okay, let me write one more statement of simplification here. You will find it will be, you will find it will be mgx plus. Now I'm simplifying the second part, which is equal to mgh and minus mgh. Okay, I have just solved these brackets here. Mg in the bracket h minus x. I have solved it, so it becomes mgh minus mgx. Okay. Now here you will find that my mgx and mg minus x minus mgx plus mgx and minus mgx will get cancelled. So what I am left with? So you will find we are just left with mgh. So how much is the total energy at point B? The total energy at point B is mgh. Remember what was the total energy at point A? At point A, the total energy was mgh. At point B, the total energy is mgh again. So what we can say, that the total energy at A and the total energy at B is still the same. If you have copied it, please type yes in the chat. Quickly type yes in the chat so that I can proceed. Sure. So let's start with the third case now. Now we are talking about at position C on the ground. Now, before starting with the derivation of sum of kinetic and potential, I want to say that at C on the ground, the object is not at rest. The object is not at rest. We are talking about a condition where the object is about to touch the ground. So it is having that velocity. It is not, it has not hit the ground and then it is at rest. We are talking about it is just about to hit the ground. Okay. So we are talking about this case. It is just about to hit the ground. So let's start with the kinetic energy derivation. So we are taking what is the velocity. So let V be the velocity acquired by the body at C. How much is the velocity at C? The velocity is V. And how much is the distance it has fallen? So it has fallen the distance h. So what is my initial velocity? 0. How much is the displacement? The displacement is h. And how much is the acceleration due to gravity? The acceleration due to gravity is g. Okay. So from the equation again, v square is equal to u square plus 2s. You will find v square is equal to u square. U square value is 0. So what is my v square? My v square is coming out to be 2g. How much is my v square? You will find our v square comes out to be 2gh. How? Because v square, u square is 0, 2. A is nothing my, but it is g. And how much is the displacement? So the total displacement is, it has fallen through a height h. So my displacement is h. So my v square becomes 2gh. I am using the same rule. So kinetic energy is half mv square. So instead of this v square, I am going to substitute 2gh. So you will get half m 2gh. Now again the same thing will happen. This 2 and this 2 will get cancelled. So what we are left with? We are left with mgh. So how much is the kinetic energy at C? So the kinetic energy at C is mgh. Okay, remember this. How much is the kinetic energy at C? Now at C, just before hitting the ground, how much is the height? So at C, the height from the ground is 0. So at C, the height is 0. So how much is the potential energy? The potential energy, the formula we know, mgh, and h is 0. So obviously the moment h is 0, the remaining entire terms becomes 0. So my potential energy is 0. So how much is the total energy? Kinetic plus potential. My kinetic is mgh and my potential is 0. So how much is the total energy? So you will find for the third case at C as well, you find that the total energy is still mgh. How much is the total energy? You will find the total energy is still mgh. So if you conclude from the sum of the kinetic and the potential at A, at B, and at C, you will find at A, I shown you at position A, the total energy was mgh. I had given 1 star. Then at B, I shown you that the total energy is still mgh, 2 stars. And at C, again, the total energy is mgh. So what we can conclude? We can conclude that during this fall, during this free fall, the total mechanical energy was conserved. Means it was same, it was constant. Yes, there was an interchange. You find that the potential energy was decreasing and the kinetic energy was subsequently increasing, but the total energy was same. Please copy this link. If you are done, please type yes in the chat. Thank you then. I will stop sharing this. Now, we will look at some more applications of it. Okay, this is now again a very interesting idea. We are looking at some more applications of this. Okay, look at this. All of you. Look at this. This is a very basic and fundamental explanation of law of conservation of energy. Let me explain you about this simulation. So what we are having a skater's track. This is the track on which this skater will skate. Okay. Now, right now I start. So this is my bar graph, which will show you the kinetic energy and potential energy. This is my speedometer, which will tell us about the speed of the skater. And this is one of the type of chart. Okay, I will add on that chart later on. Okay. Now, see, right now, how much is the total energy in the system? So no energy because this skater is on the ground. So the potential energy this skater is having is zero. Why? Because potential energy is empty. The potential energy is zero. And how much is the kinetic energy? So if you look at this skater, it is at rest. So that's why the kinetic energy is zero. Now what I'm going to do? I'm going to lift this skater. The moment I lift this skater, you will find its potential energy will increase. Why? Because it will be above the earth surface. See, as I am lifting, see what you find. Look at the bar graph. What you find, the potential energy is increasing. So this object is having some potential energy. And how much is the total energy? The total energy is all potential energy only. So I lifted that object to a height. Clear? The moment I lifted it, its potential energy is increasing because right now this object is having some potential energy. Clear? How much kinetic energy? Zero. Okay, so that's why you find the total is all potential. You find that the blue is potential. Now, what will happen? Now I'm going to release this skater. I'm holding this skater right now. So I'm going to release this skater. And the moment I release it, okay, let's observe what actually happens. Okay, as I release it, you just look at the change in the kinetic and the potential energy. Okay, so I release him. Okay, see what's happening. So you will keep you will you will find there are so many changes taking place. Okay, but I will do it in a slow motion and then I will explain this. So I'm doing it in slow motion. In fact, I will pause it as well. So one by one we will focus on what's happening. Okay, so we start with from the top. On the top I will pause it. Now see, at the top you will find this skater is only having potential energy. Why? Because at the top you will find this object momentarily comes to rest because the velocity is almost zero. So at the top the potential energy is maximum and the kinetic energy is zero. Now as the skater will fall, you will find its potential energy will decrease. Why it will decrease? Because the H parameter will keep on decreasing. But what will happen to the kinetic energy? Yeah, that's what I'm saying now. Okay, I'm sorry if I said something wrong. Okay, I'm repeating it, Arnav. I'm saying that now at this position, its potential energy will keep on decreasing. Why? Because its height the height will keep on decreasing. But at the same time, what will happen to the kinetic energy? The kinetic energy will increase. See, it's falling. See, You find, see, the kind potential is decreasing and the kinetic. Look at the graph part. You find the potential is decreasing and the kinetic energy is increasing. Yes, see, the kinetic energy is increasing and the potential is decreasing. Now we will talk about this position at the ground. See, at the ground, what happens? So at the ground, you will find it has all kinetic energy. And how much potential energy? Potential energy is zero. Why? Because the height from the ground is zero. So as the object is falling, your potential energy is decreasing and kinetic energy is increasing. So at this position on the ground, the potential energy is zero and the kinetic energy is maximum. But what will happen? The object will not stop there because it is having kinetic energy. So it will again start moving up. See, as the object is moving up, you will find its potential energy will keep on increasing because the height is increasing. And what happens to the kinetic energy? So the kinetic energy is decreasing. Why it is decreasing? Look at the speedometer. The speedometer will show the speed is getting decreased. See, look at the speedometer. Look at the speedometer. Clear? You find that as it rises up, the speed decreases, so the kinetic energy decreases and the potential energy increases. Let's do it again. See, kinetic increasing, potential decreasing. Okay, then going up, kinetic increasing, potential, sorry, kinetic decreasing, potential increasing. And what we observe? We observe that this energy conversion will keep on taking place. If you want, we are having a pie chart. So look at this color now. Okay, you will find that at this blue is of potential and the other is of kinetic. See, at the top, it is having all potential. The blue is potential. Potential is decreasing, kinetic is increasing. Here, all kinetic. Then again, you will find that the potential is increasing and the kinetic is decreasing. So in this way, there is a conversion taking place from the kinetic to potential and potential to kinetic. Okay, you can keep on, you can see that it's going on, it's going on. Yes, very good, Harshu. The mass of the skater will affect na beta. Okay, if the mass of the skater is less, the kinetic energy as well as the potential energy will be less because mass is a parameter, Harshu, which is there in kinetic as well as potential. Yes, what's the formula of kinetic energy? Half m v square. So mass is there. What's the formula for potential energy? M potential energy mgh. So m is also there. So definitely, I will show you that. I will decrease the skater of the mass. I will decrease the mass of the skater and you will find the difference. Okay. So can you see this? So you will find that the kinetic energy and the potential energy is changing. It is there's an interchange between kinetic and potential, but the most important thing is the total energy is remaining constant. Okay. Now I will show you something more interesting. I will keep it on the ground. Okay. Let me wait now. Now now I will on the grid. Now this is what I want to say. Now, as I said that energy can neither be created nor it can be destroyed. So now we'll talk about the creation. Okay. So I lift it and you will find that I have lifted it from this height. Look at the line, the grid. Okay. It is between 4 and 5. Look at the grid line. It is at 5. Okay. So I am dropping it from 5. So you will find on the other end, the object will not rise beyond 5. It's been dropped. So here you will find it will not rise beyond 5. Here also it will not rise beyond 5. Why? Because the total energy is same. So it will not rise beyond 5. Okay. But if I do one thing, okay, I pick it up, okay, and I'm dropping it from internet. Keep it here. Now I lift it and from where I'm dropping it from this height. So what will happen? Now see, I started, I dropped it. What happens? The skater. What happens? The skater is jumping over. Why? Because it is having more energy. So the skater will jump over, okay, because it is having more energy. Getting it? But so try to understand now. If I lift it and I keep it here at 2 meters, this is at 2 meters. Okay, at this place, 2 meters, you will find it will not reach beyond 2. It will not reach beyond 2 because how much is the energy here? the same because there is no energy being created. Clear? Now, I take it here. Now, Harshu has asked her, will the mass affect? Okay. Now, see, I'm lifting this, and as I am lifting, you will find that the energy, the potential energy is also increasing. Okay. But now, remember the length. Okay. It is, if you remember till what is the magnitude of potential energy. Okay. Now, I will decrease the mass of the state. I'm decreasing the mass of the state. Now what will happen? See, I lift it to the same height, but look at the maximum potential energy. Why? Because the mass of the skater is less. Okay. If I increase the mass of the skater, okay, now see how much is the, see it's going beyond the length. See the energy is going beyond the length. And the same way, when I will decrease it, you will find that the mass is changing, and that's why the kinetic and the potential energy is also changing. Okay. So definitely it affects. Now, when we do it, okay, let's take a practical part of it. See, you will find there's an energy conversion from kinetic to potential, potential to kinetic, kinetic to potential, potential to kinetic. But in actual, we never find this. Okay. In actual, you will find that, assume if you have done skating or you have seen skaters, you will not find that the skater will keep on skating forever. Assume I don't stop it. So what will happen? This skater will keep on skating forever. But in real life, do we find something like this where the skater is doing the skating forever? No. In real life, we don't observe this. Okay. Because in real life, we have some very interesting parameter involved. Okay. So I will pause it now. Okay. I will pause it. And let's talk about a real life scenario. What happens in a real life? Everything is same. I turn on the bar graph. Okay. I can turn on the speed as well. Okay. And let's look at what happens in real life. Okay. Now, here I will lift it. Its potential energy is increasing. And now you'll find there is a conversion of kinetic to potential, potential to kinetic. And this keeps on going. This continues. This continues. The total energy, the kinetic and the potential energy is changing. It remains. But in real life, what happens? In real life, we don't find this. Why? Because in real life, you will find there is a friction involved. There is a friction between the skater and the track. Right now, if you look at this part over here, the friction is off. Now, what I will do, I will turn on the friction. Okay. So, I will stop it. I will keep it here. And now I will turn on the friction. The friction is on now. So there is a friction between the skater and the track and the skater. Okay. Now see what happens. And I want all of you to focus on the thermal part now. See, I'm lifting it. So again, the same potential and all total. Now I drop. See, I play it now. See what happens. Look at the thermal part. See what happened. What happened? The entire energy, the entire potential energy is being converted into thermal energy. Why? Due to the friction, the entire energy is being converted. Otherwise, you may be wondering that where that energy has gone. Now the object, this skater is at rest and on the ground. So it is at rest, so the kinetic energy is zero, and it is on the ground. So the potential energy is also zero. The skater is having zero kinetic and zero potential. So what about the initial energy we have supplied to the skater to lift him up? The energy what we have supplied to the skater to lift him up has been converted into the thermal energy. Clear class? So you will find that the total energy will get converted into thermal energy. So this is what you will find in a real life scenario. Okay, so let me do it again. So I lift it, I'm lifting it. See, let me do it in slow motion. So we will understand how the thermal energy parameter is increasing. So I lift it. Okay. Now I drop it. Okay. So the moment I drop it, see, look at the thermal. See how thermal is increasing. Thermal is increasing. Gradually the thermal has increased, and again the thermal is there. It's increasing very slowly. But when it is close to the earth, because of there the friction is more, and the thermal is increasing to the greater extent. Exactly. So you will find that how the thermal energy or the total energy is getting converted into thermal energy. Exactly. So this is something what actually happens in day-to-day life. There is friction and the energy is been getting converted into heat energy or thermal energy. Clear? Now, Aditya is saying, sir, show what happens when we take the track as W. So this is our track. Okay, so I will first, I will make the friction off. Now, in fact, I will use the grid as well. So I'm placing the grid here at 5. Okay, at 5. I will place the grid. Wait a minute. Oh no, wait. Let him lift up. Here I am placing it. Okay, now here I place him. Okay, so it is having all potential, no kinetic. Now see what happens. So what happens? It will reach, and what's the only difference you will observe? You will observe that here the kind potential. So I'm sorry. I think it was little more than the previous. That's why he fall. So let's clear it. Now I will lift it again, and I will lift it in this side. This is a convenient. Sorry, this is a convenient. Let's not. Now see what happens. It will reach till 5. Sorry. So what we observe, the only difference you will find that here, here you will find now at this point it is having all potential. Okay. At this point all potential. Then the potential is decreasing and the kinetic is increasing. And at this very moment you will find that the potential is 0 and the kinetic is maximum. Okay. And then as it rises here, you will find that here it has some kinetic and some potential. But here at this point, it will not have all kinetic and 0 potential. This is what you will find. At this point, it is not having all kinetic. It is having some kinetic and some potential because it is at a height. And then again, you will find that the potential will increase. So this is the only difference you will find here. Otherwise, the rest is the same. Okay. See the track. Aditya, that's your query na beta about the track. So this is how the energy will change. And if I turn on the friction, okay, let me do it in normal condition. Okay. Now I will turn on the friction. See, I will turn on the friction, or let me do it in slow motion. That's okay. Let me do it in slow motion. I turn on the friction. I turn on the friction class. See what will happen. Oh, wait a minute. I have not turned it on. Friction is on, but I've made it 0. So let me turn it on. I will do it at the top when the potential is maximum. Okay. Now I'm going to increase the friction. Yes. I've added the friction now. See. I've added the friction and see. Yes. But now it will not come back to that point. No, sorry. Now it will not reach to that point because the friction is not enough. The friction is increasing and the energy. And what will happen? See, very interesting. What you will find? It has some potential. Okay, the kinetic is 0, but it is above the ground. So it has some potential and the rest is half. Okay, so this is how the energy will change because it is at half. But if he stops in this part of the track, then here you will find it will all thermal and zero kinetic and zero potential, because here it is on the ground. Okay, class? I hope your idea is very clear now. Okay, let me share one more thing with you. I will stop this now. Now this is my pendulum. Okay, now again, look at the same concept. Okay, now I am taking the pendulum, I extend it to 30 degree. Okay, and I release it. Okay, let me magnify this. Look at it. Let's do it in slow motion again. Okay, what do you observe? See, this is the extreme position of the pendulum. What we observe at the extreme position? At the extreme position, we observe that the pendulum is having all potential energy because it is obviously at a height above the ground. Okay, try to understand. It is at a height above the ground. So it is having all potential and zero kinetic. Why zero kinetic? Because you will observe it carefully. The pendulum comes momentarily at rest. The pendulum, it comes momentarily at rest. Okay, so that's why you will find that the kinetic energy is zero. Okay, and the potential energy is maximum. But then what happens? See, as it is coming, you will find its kinetic energy is increasing and the potential energy is decreasing. See, kinetic energy is increasing, potential energy is decreasing. And here at the mean position, what do you observe? You observe that at this mean position, the height is zero. The height from the ground is zero, and that's why the potential energy is zero. What about the kinetic energy? The kinetic energy is maximum because the height is minimum, so the potential energy is zero and the kinetic energy is maximum. Means it is having maximum velocity at this very point. See, it is having maximum velocity. Then it is reaching, and you will find it is having maximum potential, zero kinetic. And you will find, see how the kinetic and potential is changing. So you will again find that at the extreme position, it has maximum potential energy and zero kinetic energy. And at the mean position, it has maximum kinetic energy and zero potential energy. So you will find that it is getting converted from kinetic to potential, potential to kinetic, kinetic to potential in this format. You'll find there's an energy conversion from kinetic to potential and potential to kinetic. Okay, but again the same question arises. If I keep a pendulum oscillating, you will find the pendulum will keep on oscillating forever. Yes or no? The pendulum will keep on oscillating forever. The pendulum will not stop. But in real life, if you take a pendulum and if you make it oscillate, you'll come to know that the pendulum will never ever, the pendulum will never ever continue to oscillate. It will eventually stop. Okay, but in this simulation, again you find that it is not stopping. So why the pendulum is not stopping? Okay, it is due to the, because this pendulum has no friction. Friction means air resistance in this case. Okay, so that's why the pendulum is oscillating. But if you, in real life, we see that the pendulum is oscillating in air and there is air around it. So the same way, what I will do, I will add some air to this surrounding. I will add some air around this pendulum. Okay, now see what happens. Look at the parameter of thermal now. Huh? So I'm adding some friction. So as I've added some friction, you will find the amplitude of the swing is decreasing with time. The amplitude of the swing is decreasing, and look at the thermal energy. The thermal energy is increasing. Okay. So what happens to the energy? You will find the energy is being converted. The total energy is getting converted into thermal energy. So that's the reason why the pendulum stops oscillating. Why? because of the air around it. If you take a box, okay, a box made up of glass, and if you remove the air from that box, if you completely remove all the air from that box, and if you take a pendulum and if you make it swing in that box, you will find that the pendulum will keep on oscillating forever. Okay. Now, Harshu is asking, sir, when will the kinetic and potential energy would be equal? It will be somewhere in between, beta. Okay, see. So I will make the friction null. Okay, I will make it oscillate at 20 degrees. And now, somewhere in between, I will do it in slow motion. And somewhere, wait a minute, I will pause it. It will be somewhere in between. See, we are very close to the see, it is somewhere here in between the swing. You will find that the kinetic and the potential will become equal. Okay, so that's okay. That's not a big. So you will find it. It is coming out to be equal somewhere in between the swing. Okay, not on the extreme, not at the mean, but somewhere in between. Okay. Now I will just show you one thing where I want to say you. Okay. Now look at it. This is my energy graph. Okay. Now I move it on the other end. So I keep it here. Let me pause it. Now, what I'm doing, okay, I will increase the mass. See, I'm increasing the mass of the bomb. Look at what happens to the potential energy. See, the potential parameter is increasing. Let me magnify it a bit. Now see, I'm increasing the potential energy. See, I'm increasing the mass. See what happens to the potential energy. The potential energy is increasing. I decrease the mass of the bomb. See what happens to the potential. The potential energy is increasing and decreasing as I'm changing the mass of it. Okay, remember this because the mass of the bomb again plays an important role. Now we have to discuss one more important thing. I told you it has a maximum velocity or speed at the mean position. So we have a velocity parameter. Okay, can you see the velocity parameter? Okay, if I want to show you, I have to reset it, and I will make it little more so that its velocity will be more. Look at that velocity. Look at this. Can you see this uh, green arrow? That arrow is a velocity. See, can you see the arrow? See the size. Velocity is a vector quantity. So velocity has magnitude as well as direction. So look at the direction of the velocity at the mean position. But I want you to emphasize on the size of this arrow. You'll find that the size of this arrow is maximum at the mean position. See, now the size of the arrow is decreasing, 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 decreasing. Here it becomes almost zero. Why? Because the velocity suddenly, because the object comes to rest. Okay, now see, the size of the arrow is increasing, increasing, increasing. And at this position, you will find the size of the arrow is maximum. Then again, the size of the arrow is decreasing. This size of the arrow is a parameter of velocity. So you will find that the velocity is maximum, and that's why the kinetic energy is also maximum at this position. Getting it, class? The kinetic energy and the potential energy is changing. You will find that the interchange, but why the kinetic energy is maximum at the mean position? Because the velocity is maximum. And as we go up, the kinetic energy is decreasing. Look at the length of the arrow, and at the extreme position, you will find that the kinetic energy is zero and the potential energy is maximum because the velocity has almost disappeared. Okay, and at the mean position, you will find it has maximum velocity because the length of the arrow is maximum. I hope you are getting it, beta. Now I just want quickly all of you to ask your doubt through the chat. If you have any doubt, please ask me because I've shown you how the law of conservation of energy, how it is changing from kinetic to potential. Okay, and what is the difference in actual scenario and in our day-to-day life? What is the difference? Any doubts? If you don't have any doubt, please type no doubts, sir. Okay, so that I will be comfortable with this. If you have any doubt, please ask. If you have no doubt, write no doubts. Okay, so no problem. Then I will be comfortable that you are getting it, because we are going to solve a number of numericals based on this concept. Okay, obviously not today because we are running out of time, but tomorrow we will solve some more examples of this. Okay, sure. Thank you very much then. Okay.